Okay, so this is section 7.7. This is approximate integration. A couple of the topics that are in here is actually something that I cover back when I'm talking about Riemann sums, pretty much right before um, the idea of integration comes into play. Um, so it might seem like a bit of a repeat if you've already seen that in a prior section. And then there's one topic in here that is definitely something that has not been covered. So let's go ahead and get started. So we're going to use the techniques of approximate integration here. I guess one of the questions might be, why do we use approximations when we know how to integrate things? So really what it comes down to is, what if we can't integrate for some reason? What if the function is just too difficult or even impossible to integrate using the antiderivative techniques that we already know? And later in the course, you will actually see that there are definitely functions which are very difficult to do by our standard anti-differentiation techniques. Or probably this is the most important reason, is maybe the function is determined by real life empirical data and there's no exact formula for the function. That is probably the most common reason. And if that's the case, then obviously what we want to do, if we've got all this real life data, we want to come up with the best approximation that we possibly can. And then there's several different methods that we can do that. Now, again, if you've already seen this, because I do the midpoint rule as well as the trapezoid rule back when I do Riemann sums. I do them all together. I just don't see any reason not to put it all together at that particular point. But if for some reason, you have not seen that, or Pac-Man just died. Um, if Sorry, that just kind of threw me off there. Um, if for some reason that you haven't already seen this, then we'll go ahead and get through it now. So if you remember, the concept of the Riemann sums, the left and the right hand approximation methods, um, was that you're taking a bunch of rectangles and you're going to fit those to the curve to the best of your ability. And you can either do that by using the upper left hand corner of the rectangle to be the height of the rectangle, or the upper right hand corner of the rectangle to be the height of the rectangle. And then your base is the change of x typically. So our example here for midpoint is pretty much the same idea. I'm going to do a little sketch here. And this could be whatever function. It's probably going to look kind of like a quadratic, but it doesn't really matter what the function is. Do a function, maybe it looks something like that. This just makes it easy for us to be able to kind of visualize what's going on. So what we've got is, we want to fit rectangles in here, but we want to use um, a midpoint rule. So we still have to partition off this particular curve into different sections. In this particular case, I'm just going to make it 4 equal sections, although the n value, which is the number of partitions, could be whatever they ask for, or whatever's necessary for your given problem. So if we consider that this is the end over here, just kind of draw a little dotted line down there. And we want to partition this thing off into, like I said, 4 equal sections. I'm going to do my best here to figure this out. This looks like that might be the middle, and there, and there. Close enough. What we have is this piece right here, well, all these pieces actually, and I didn't draw it specifically that well, but this is going to be your change of x, which really in this case just represents the base. It's going to be the base of a rectangle. Now, the rectangle that we draw needs to be from the center or the middle of each one of the partitions. So if you kind of put a little dot, like right here, right there, and right there, that represents the middle, or in between, or the average of the x's, if you want to call it that, um, for each one of these things. So what we would do is, I'm going to try and use maybe the second one here so that it's kind of out of the way. We would call maybe this particular one x sub I. It could be x, in this case it's x sub 1, or x sub 2, I guess. X sub 1 or x sub 0. It depends on if you start at 0 or 1. But x sub 1 would be the first one, x sub 2, then x sub 3, then x sub 4, then x sub 5 would be your last one out there where the green dotted line is. But in general, the sub I just means it's some kind of an indicator. And then this one over here, of course, would be the next one, so it would be x sub I plus 1. If I were to take those two things and average them, that's just x sub I plus x sub I plus 1 divided by 2. Well, that's what we call x bar sub I. It's actually a notation more from statistics, but the bar just means the average. So that little bar on top of the x means the average. So we're just going to average those, and that would give us this piece right here. This would be x bar sub I right in the middle. Okay, it's really not this difficult. I'm just giving you the actual mathematical notation, but basically you're just taking the halfway point in between those two blue lines there. To figure out your delta x in blue over here, delta x is going to be whatever the difference in your endpoints is. So if this is b over here and this is a over here, it's just going to be that delta x is b minus a, and then we're going to divide it by however many partitions we have, and then that's going to give us the actual delta x. It's going to give us the change of x. So in this case, for example, let's just say a is 0 and b is 1. If you're going to split up the difference between 0 to 1 in 4 equal partitions, it would be 1 minus 0, which is 1, over 4, or 1/4, 0.25 for each partition. That should make sense to most of us. How we actually find the midpoint is going to be, let's go with red, I guess, since we use that. We're going to extend from the red dot up to the function. And we're going to put a dot in the same place on the function that the red dot appeared horizontally on the bottom. So we're going to do that in all these places. And basically, I'm going to create my rectangle now through that dot. So basically, it's going to be, okay, that's the top of my rectangle now, and I'm going to bring it straight down the partition. And there's your first rectangle using the midpoint to find the value of the function's height. And then I'll do the same thing here, right through there. Same thing right through that one horizontally. And then the last one actually looks really long comparatively, but again, that's okay. So the formula to find the midpoint approximation here, and we'll call it like m sub n or something like that. I don't know. We'll just call it the midpoint. I'll just say the midpoint approximation. You know what? I better bring this down here because I don't think I'm going to have enough room to write it there. Midpoint approximation method. You actually see it listed as MRAM, M-R-A-M, midpoint Riemann approximation method. I'm just going to call it midpoint. Is going to simply be delta x, that's the base, times the height. Well, if delta x is consistent, we can factor out the delta x's, and we can just multiply it by the sum of all the heights, which is going to be f of x bar sub 1 plus x bar sub 2 plus dot 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 all the way up to the last one, which is going to be f of x bar sub n. Again, just think of this as base height. That's all it is. Base times height. And if you were to distribute the delta x there, you'd have base times height plus base times height plus base times height. You're adding up all the areas of the rectangles. Okay, really not too difficult. Very simple to do. Biggest thing is just figuring out your delta x so that you know where the red lines are. Excuse me, originally there were blue lines, and then figure out what the middle point of the x values is to find the function's value. When you see the example, you'll see this is pretty easy. All right. The second one is the trapezoid rule. Again, this is something I show when I do the other three, but we're going to go ahead and do that right here. So we will do another sketch. And the trapezoid rule, I'm going to pretty much try and use the same overall type of function here. Something that looks like that. Again, it just makes it easy to do. If this is the end, if this is our B, oops, lost my dots. So we'll call that B, we'll call that A. Once again, I'm going to go with 4 partitions. Again, doesn't have to be. be whatever number they want, but we'll split this up into four, oops, it's supposed to be more vertical than that, four equal regions. The idea here is we're going to form trapezoids. In order to do that, you're basically going to connect the dots at each one of these places where your partition hits. And we're not going to connect them in a smooth curve. We're going to connect them with straight lines. So it's going to look like that. Like, oh, that was not straight at all. More like that. More like that. And as you can see, this was not very well drawn. This is horrible, actually. I'm having a real hard time with the straight line idea. But what you can see there is that the less curved your function is, the closer those lines are going to be to the actual curve itself. So your approximation here is going to be pretty strong the less curved it is. Now, the more curved the line is, or let's say the more concave that it is, that's a term we should all know at this point, the less the approximation is going to be accurate. But it's the same general idea. So what do we need? Well, if we're going to use trapezoids, we need to know what the area of a trapezoid is. And the area of a trapezoid, if we recall, is 1/2 the sum of the two bases of the trapezoid times the height. And the biggest thing is, well, what's the base and what's the height of a trapezoid? So if you remember the rules, the trapezoid's height is perpendicular to both of the bases. Well, that actually means that the delta x portion is your height. This delta x is the height of the trapezoid because it is perpendicular to both of my bases, and then your bases are parallel to each other. Okay, it's not the sides that are I guess you would say skewed to each other, but the two sides that are non-parallel are not considered bases. So technically out here we would have base 1, this would be base 2. Notice base 1 really doesn't have any height, it's a 0. This is base 3, base 4, base 5. So we have 5 bases to consider. How do we find delta x, or the height? It's the same as we did before. Delta x is going to be b minus a over n. And again, that is the same in this case as your height. All right. So if we want to do this, we want to add up all the areas of the trapezoids. Well, again, areas of trapezoids are 1/2 the sum of the bases times the height. So we would have the area of this particular one would be 1/2. Well, let's see. The first trapezoid, this one right here, has base 1 plus base 2 times the height, which is delta x, plus the second trapezoid is this one right here. It is 1/2, and this time it'll be base 2 plus base 3 times the height, which is delta x, plus 1/2 base 3 plus base 4. Okay, that's this one, times the height, delta x, and then the last one is this one right here, which will be 1/2 base 4 plus base 5 times the height, delta x. So the reason I wrote this one all out like this is because I want you to be able to see there's something in common here. If the delta x's are the same, and in this case we are given that they are, they won't always be in real life circumstances, but in this case they are, and we know 1/2 is a constant, you can pull those things out to the front. 1/2 delta x can be factored out. All you have left now are the sum of the bases. And what I have is base 1 plus base 2, base 2 plus base 3, 3 and 4, 4 and 5. What you should notice, and hopefully you already have figured this out, is that some of those bases are being added twice. I can see that base 2 is added twice. I can see that base 3 is added twice. I can see that base 4 is added twice. The only ones actually that are not going to be added twice are the ends, base 1 and base 5. So what I know is that I should be able to multiply 1/2 delta x, because that's factored out front, by the sum of base 1 plus the last base, whatever that's going to be in general, will be base sub n plus, and then all of the interior ones, in this case my 2, 3, and 4, those are all going to happen twice. So I'm going to have multiply 2 times the sum of all of the interior bases, which is going to start with your second base. Whoops, didn't mean to erase that. Plus the third base, plus dot, 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 all the way up till the base right before the last one, which is the n minus 1 base. And that's how you're going to use your trapezoid rule to be able to figure this out. All right. This video, I think, took a little bit longer than I was hoping it would, so we're going to come back with a second video. It'll probably be about the same length or so. We'll do the example using the actual trapezoid rule and midpoint rule. We're going to talk about the idea of error, although we're not going to go into a lot of specifics on how you bound the error, but we're going to talk about error. And then we're going to do the last of the rules, which is called Simpson's rule, which is something new that has not been taught in a prior video.